Welcome back. Today we're going to cover section 9.3, which introduces rational expressions, and we talk about how we can multiply rational expressions or divide them. First off, what is a rational expression? A rational expression is nothing more than a fraction in which the numerator and denominator are polynomials. For example, x plus 3 over x minus 2. Binomial over binomial. X squared plus 5x plus 6 over x squared plus 4x plus 3 in the middle. Quadratic in the numerator, quadratic in the denominator. They do not have to have the same degree, numerator and denominator, like the example that's in red, the x cubed minus 1 over 2x. We have a cubic binomial in the numerator, and we have a linear monomial in the denominator. There's no restrictions here. We can have different powers of x in the numerator and denominator. We can have different numbers of terms. But the one thing that we need to keep ourselves aware of as we work through these problems is we want to keep an eye on anything that would cause division by 0. And in the case of x plus 3 over x minus 2, this is real simple. We're just going to take the denominator, the x minus 2, and set it equal to 0. X minus 2 equals 0 means that x equals 2 is a problem, and hence my statement here that no matter what we do, we can't let x be 2, because as soon as we do that, we have division by 0, and as we know, when we divide by 0, the world spontaneously combusts and we all die. So there will be no dividing by 0. This gets a little bit trickier with the quadratic. We're still going to do the same idea. We still want to set the denominator equal to 0 and figure out what values of x would cause us to get 0. How are we going to do that here? If you said that we're going to factor, you're exactly right. We're going to factor. And so as we factor the denominator, x squared plus 4x plus 3 factors as x plus 3 times x plus 1. And then we'll take each of the factors, the x plus 3, set it equal to 0, and find, well, we'd have a problem if x is negative 3. And then we'll do the same thing with the x plus 1. And when we set that equal to 0, we find that x cannot be negative 1. And that's why we end up making the conclusion here at the end that no matter what we do with this, we can't let x be either of those two numbers. Don't let it be negative 3, don't let it be negative 1. So there's another benefit of factoring, that if you're quick factoring the numerator in your head, you might be able to see what's about to happen here. We know that the denominator factors as x plus 3 times x plus 1. We just did that. But you'll notice in factoring the numerator that x squared plus 5x plus 6 factors as x plus 3 times x plus 2. Oh, would you look at that? We have a common factor in the numerator and denominator. And just like we would do in a numerical sense, if we had the fraction 3/6, we would reduce that to 1/2 by dividing the numerator and the denominator by 3. In other words, canceling out the factor of 3 that's common. We're going to do the same thing here. So goodbye to the x plus 3, top and bottom. And we will make the statement that x squared plus 5x plus 6 over x squared plus 4x plus 3 is equivalent to the statement x plus 2 over x plus 1. That's simpler to work with, isn't it? We still have the domain restrictions. Don't lose track of the fact that we still can't let x be negative 1 on account of the fact that we would still have division by 0. But in order to make this truly equivalent to what we started with, we also have to keep in the fact that we don't want x to be negative 3. Because we could, in theory, plug negative 3 into this expression, the one that we'd simplified to, and we would have, let's see, that would be negative 1 in the numerator and negative 2 in the denominator, and that makes 1/2, and that's not equivalent to what we started with, because if we plug negative 3 in up here, we would get division by 0. So we still need to say negative 3 is not allowed. We can even expand this idea to the multiplication of two rational expressions. We can take the x squared plus 5x plus 6 over x squared plus 4x plus 3. We've already factored that. We know where that's headed. And we could multiply it by, let's say, x squared minus 2x minus 15 over x squared minus 4. And we still want to factor everything. And we know, we already have established here, that the first fraction is x plus 3 times x plus 2 over x plus 3, x plus 1. We already had that. Well, let's factor the second rational expression. X squared minus 2x minus 15, the numbers that multiply to make negative 15 and add to negative 2 are negative 5 and positive 3. So we'll rewrite this as x minus 5 and x plus 3. The denominator is a perfect square. It's the difference of perfect squares. So we can rewrite that as x plus 2 times x minus 2. If you didn't see the difference of squares, here you would say, okay, what two numbers multiply to negative 4 and add to 0? Pretty simply, that would be 2 and negative 2. Now, things we know. We already knew that we were going to get rid of the x plus 3 top and bottom. But there's one more thing we can do here. It's okay that the x plus 2 in the numerator is from one fraction and the x plus 2 in the denominator is from another fraction. That's okay, because at the end of the day, when we multiply, we've made it one big happy fraction. So say goodbye to the x plus 2 here and here. And what we've simplified this down to is what remains. And we would say that this is equal to x minus 5 times x plus 3 all over x plus 1 times x minus 2. And we still need to make sure that we've addressed the division by 0 part. So things we cannot let happen. We cannot let x be negative 3. We cannot let x be negative 1. We cannot let it be negative 2. And we cannot let it be positive 2. So here are our domain restrictions. X is not allowed to be negative 3, negative 1, negative 2, or positive 2. Otherwise, we will have a problem. Okay, this one's your turn. We have x squared minus 11x plus 24 over x squared minus 18x plus 80, and we're multiplying that by x squared minus 15x plus 50 over x squared minus 9x plus 20. Remember, factor both numerators, factor both denominators, cancel what you can, and also remember at the end of the problem, address the values of x that we can't have, what the domain restrictions are. Okay, so we start our work with factoring, and we'll factor the first numerator. That's pretty straightforward. The two numbers that multiply to positive 24 and add to negative 11 are negative 8 and negative 3. The first denominator factors as x minus 10 times x minus 8. Negative 10 times negative 8 makes positive 80, and negative 10 plus negative 8 makes negative 18. That's where that's coming from. We go to the second numerator. X, let's make that fraction bar look a little nicer. We have x squared minus 15x plus 50. This factors as x minus 5 times x minus 10. And the second denominator will factor as x minus 5 times x minus 4. Negative 5 times negative 4 makes positive 20. Negative 5 plus negative 4 makes negative 9. So we have effectively factored both numerators and both denominators. And so now let's cancel out common factors that we have. The x minus 8 top and bottom are gone. We have an x minus 5 top and bottom. They're gone from the same fraction in both cases. And again, as I said before, since we really have one big fraction now, we can cancel from one denominator, is where I crossed first, and one numerator. And all that we're left with here is x minus 3 over x minus 4. And all those domain restrictions that we've talked about before, we still have to cover those. X is not allowed to be 10 or 8 or 5 or, for that matter, 4. We don't want x to be any of these numbers. Don't let it be 10, 8, 5, or 4. So if we can multiply rational expressions, it would stand to reason that we can also divide them. And the only thing that's different here, well, aside from the fact that we have to remember how to divide with fractions, the only other thing that's different here is we have one more place that we have to look for division by 0. If we had division by 0 here, in other words, if we had 3 or 1, negative 3 or negative 1, we'd have a problem. We'd also have a problem if this were negative 1, if x were negative 1 here. But that's because we're causing one of the fractions to be something over 0. We're never allowed to divide by 0, and 0 over something is 0. So we also need to address what the numerator is in the divisor. We also have to pay attention to that. So how do we divide? Well, the first thing to remember is that this is division of a fraction is really multiplication by the reciprocal. So I'm going to rewrite this. We're going to do a little bit of editing here. And we're going to change the divisor from x minus 2 to over 3x plus 3 into 3x plus 3 over x minus 2. And we're going to get rid of this. We're going to get rid of this. And we're going to say that this is really multiplication. And so now we can go ahead and factor. First numerator factors is x plus 4 times x minus 2. We've played with x squared plus 4x plus 3 before. We know that that's x plus 3 times x plus 1. We're multiplying by the reciprocal of the original divisor. So now we have 3x plus 3 in the numerator. And we do have a greatest common factor that we're going to pull out. That's the greatest common factor of 3. 3x plus 3 is really the same thing as saying 3 times the quantity x plus 1. And there is no factoring to be done in the new denominator because x minus 2 just is what it is. All right, let's go factor canceling now. And I see an x minus 2 and an x minus 2, top and bottom. I also see an x plus 1 that can go away. And as it turns out, we're going to finish with 3 times x plus 4 over, the only thing left in the denominator here is this x plus 3. And so we finish at 3 times x plus 4 all over x plus 3. I may or may not have mentioned this before. It is not necessary for you to multiply back out the numerator or the denominator. In fact, it might be useful for you for future work to keep them the way that they are. So we'll just leave it here and say that the answer is 3 times the quantity x plus 4 over x plus 3. Remember that division by 0 will cause us a problem, so there shall at no point be permitted an x to be negative 3. We also wouldn't want it to be negative 1. We also wouldn't want it to be positive 2. But there's one more place to look, and that's up here in the first numerator, or excuse me, the second numerator. Anything that would cause the second numerator to be division, would cause this to be 0, would have caused the original problem where we had fraction divided by fraction, would have caused a division by 0 there. As it turns out, there's nothing new to discover here because everything that wasn't a constant has canceled out. You're never going to get 3 equal to 0, so we don't have to worry about that. And the x plus 1, if that's the only way to make that 0 is for x to be negative 1, but we already had that. So we're done. X cannot equal, let's make that say not equal, x cannot equal negative 3, negative 1, or positive 2. One more time, and this is all you, and yeah, I threw in a couple of extra, some extra fun factoring here. We have x squared minus 1, so we have a difference of squares, over 2x squared minus x minus 1, and we're going to divide that rational expression by the rational expression x squared minus 4 over 2x squared minus 3x minus 2. First thing you want to do here is flip that second fraction. But at the same time we do that, I'm also going to take care of the factoring. We'll kill two birds with one stone. X squared minus 1 factors as x plus 1, x minus 1. 2x squared minus x minus 1, that is 2x, clean that up a little bit here. It's going to be 2x plus 1. 2x plus 1 times x minus 1. X squared minus 4 becomes our new denominator, and that factors as x plus 2 times x minus 2. And finally, the 2x squared minus 3x minus 2. That becomes the second numerator, and that factors as 2x plus 1 times x minus 2. And one more time, for the good of the order, anything that's causing division by 0 in the first denominator, as was given to us, will be reason for us to strike out, so we're going to have to pay attention to that. Anything that's causing division by 0, that would cause this to be 0, is division by 0, and anything that's here would be causing division by 0 if it makes x squared minus 4 equal to 0. So we've got 3 places to look, and we'll do that on the subsequent slide. Looking one more time for common factors across the numerator and denominator, and I see that 2x plus 1. See ya. We also have an x minus 1 paired up in the numerator and denominator. And while we're at it, we'll also take care of the x minus 2 that's in the numerator and denominator. And when we simplify this out, we'll get, fix that up real quick, we'll get x plus 1 over x plus 2. And anything causing division by 0 will be an issue to us. At 2x plus 1, setting that equal to 0 would give us negative 1/2, would be a problem. X minus 1, we don't want it to be 1. X plus 2, negative 2 would be a problem. X minus 2, that means we don't want it to be 2 either. So we can't allow negative 1, 1, negative 2, or positive 2. Let's make that look more like a comma. There we go. But we also had to go to the second numerator from the multiplication because that was originally the second denominator. the 2x plus 1, we already took care of that. That would be 0 if x is negative 1/2. That's already on our list. And x minus 2 would be 0 if x is positive 2. That's also on our list. And so we are done with our list of domain restrictions. We do not allow x to be negative 1/2, 1, negative 2, or 2. But the simplified version of what we just did, all that big stuff, all that factoring has led us to this conclusion. X plus 1 over x plus 2, and we need to tack on the 4 domain restrictions. So that's multiplying and dividing. Next time we'll be adding and subtracting. See you then.